Hello, this is my video lab report for Lab 3, Circuits. The purpose of this lab was to investigate the behavior of electric circuits containing resistors and capacitors. We test conservation of charge using Kirchhoff's node rule, conservation of energy using Kirchhoff's loop rule, and examine how capacitors charge and discharge in an RC circuit. Overall, our results match theoretical predictions. The current remained the same throughout the series circuit, the voltage drops followed Ohm's law, and the capacitors showed the expected gradual charging and discharging behavior. Three main physics principles were used. First, Kirchhoff's node rule states that the total current entering a junction equals the total current leaving it, which follows from the conservation of charge. Second, Kirchhoff's loop rule states that the sum of voltage gains and drops around a closed loop equals zero, reflecting the conservation of energy. Finally, Ohm's law, written as V equals I times R, relates voltage, current, and resistance, and allows us to predict voltage drops across resistors. For our experiment, we first built a simple series circuit. The circuit included two 1.5 volt batteries, a 47 ohm resistor, a 100 ohm resistor, and a multimeter that would be used as both an ammeter and voltmeter. We measured the current in the circuit and the voltage across each component. For analysis, the system consisted of the resistors, wires, and ammeters, while the surroundings included the batteries providing energy and the voltmeter used for measurements. First, we measured the current through the circuit. Both ammeters read about 18.3 milliamps, meaning the current was the same at both points in the circuit. This confirms current conservation in a series circuit. Next, we measured the voltages across each resistor. The battery provided about 2.8 volts, while the 100 ohm resistor had a drop of about 1.8 volts, and the 47 ohm resistor had a drop of about 0.8 volts. Using Ohm's law, we can predict these values. Multiplying the current by 100 ohms gives about 1.83 volts, and multiplying by 47 ohms gives about 0.86 volts, which closely matches our measured values. Applying Kirchhoff's loop rule, the total change in voltage around the loop should be zero, and using our measurements, 2.8 minus 1.8 minus 0.8 gives about 0.2 volts, which is close to zero, and that small difference is likely due to wire resistance or measurement uncertainty. In another trial, we placed an ammeter in parallel with the 100 ohm resistor. This created a very low resistance path, allowing a larger current to flow. The ammeters measured about 49.3 and 51.4 milliamps, showing how current increases when resistance decreases. We also created a potential versus position graph around the circuit. The graph shows voltage increasing across the batteries and decreasing across the resistors, with the total change around the loop returning to zero, consistent with Kirchhoff's loop rule. In the second part of the lab, we studied an RC circuit with a 1 farad capacitor and a light bulb acting as a resistor. When charging, the capacitor initially had almost zero voltage, so the current was at its maximum and the bulb was bright. As the capacitor charged, the voltage increased and the current decreased, causing the bulb to dim. During discharging, the battery was removed and the stored energy in the capacitor flowed through the bulb, which briefly lit again before fading. We found that the charging time was about 58.27 seconds and the discharging time was about 54.35 seconds. Using the time constant formula, tau equals R times C, with about 4 ohms and 1 farad, we predict a time constant of about 40 seconds, which is reasonably close to the measured times. The difference is likely due to the extra resistance in the real circuit, like in the wires and internal components. Overall, the experiment supported the key physical principles of circuits. The series circuit confirmed current conservation, and the voltage drops matched predictions from Ohm's law and approximately satisfied Kirchhoff's loop rule. The RC circuit demonstrated the expected gradual change in current and voltage during capacitor charging and discharging. Possible sources of error include internal resistance in the batteries and meters, tolerances in the resistor values, and uncertainty when measuring the charging and discharging times. Finally, we considered what would happen if a capacitor were charged with no resistor in the circuit. In the ideal model, the time constants given by tau equals to R times C, and if the resistance were zero, then the time constant would also be zero, meaning the capacitor should charge instantly. However, this does not occur in real circuits, because all real components, like the wires, batteries, and measurement devices, have some small resistance, and capacitors may even have internal resistance. Because of these unavoidable resistances, the current cannot become infinitely large, so the capacitor charges very quickly, but not instantaneously. Thank you for watching.